which is memory structures. So today we are starting to this memory structures right now. I'm going to say that now we start to memory structures. So as you know, memory is a very important element. We want to store the data, and over the years we have seen many different data storage options, and these are for external memory storage. For example, there used to be some tapes, magnetic tapes, and then these magnetic tapes started to be used in a smaller format for audio tapes, and this was initially meant for the computers, but then it was meant for audio tapes, and then there were different smaller versions of it. But there are also other categories, computer memory elements, and the memories that are used in computers are listed in different categories. One of them is read-only memories, where we just write the memory and then once, and then we start reading it. So the concept is like CD-ROM, right? CD-ROMs, compact disc ROM. So the original, let's say, CDs, it was written once, and then you just read it. So you don't change the data. Those kind of memories are called read-only memories, or ROMs. And there's another category, read-write memories. So read-write memories, you can write the memory, read it, and maybe later on you decide to change the internal content, and you can rewrite, and then you can read it again. So in this kind of read-write memories, there are different groups, maybe we can mention. Sequential memories, which we don't really follow it right now, but most important one that we'll be talking about is going to be random access memories, RAMs. So there are different RAM types: static RAMs, dynamic RAMs. So this is different two types that we'll be seeing. And after, actually, in this course, we will be just talking about the basics of this. And this is right now an industry by itself. So how to make memories, and then there is a revolution actually in terms of memories, and then the new type of memories that are today in the usage. So again, going back to history, the tapes, I don't know, your generation maybe doesn't know about these tapes, but these tapes were put into machines like this, and then magnetically it was written and then read. Maybe it's or get a chance to use, but if your parents are might have still a good collection of these kind of music storage elements. And in our times we were using these kind of floppy disks. Again, the internal storage was based on magnetic writing and reading. Magnetic heads were writing and reading. And then in our times, the CD-ROMs became an important revolution. So the CD-ROMs were really changed because the quality of the signal was very good. It was stored in digital domain. It was not magnetic. And then the quality was very good, and the noise was not there. So damaging was not that easy unless you scratch it or something. Okay. And then, this kind of memories, right now it's being used inside the computer, but externally we started to see these USB devices, and then right now inside of those USB devices, it can hold huge amount of data. And of course, there are other type of external hard disks that are available today. But in this course, we will be talking about basic what is a RAM, and then how it can be made with masks. It's called mask RAM. And then this is programmable RAM. This is mask programmable RAM. So here another type is programmable RAM. So here the programming is done once. Can we at the beginning? And the customer is not allowed to change the stored data. Basically, okay. So storing is predefined. Okay. Like previously written data is used. Okay. So why would you need that? Maybe for the operating system, for BIOS, or for predefined digital function. Okay, so basically in this one you write the mask level. The writing of the data is done in the foundry. Okay, so like the IC manufacturing. Okay, so fixed during integrated circuit manufacturing. So in the programmable RAM, people was using this let's say you want to make a refrigerator controller circuit, and then in that refrigerator controller, you know what that refrigerator is going to do, or washing machine, you know what it's going to do. So you fix the stored data, the function that it's going to be following in a memory cell, and then you put it inside and the PCB level. And then, when the power is on, it starts from the beginning and then it continues depending on the inputs, for example. So, and then, that's written once in the factory, and then it's being fixed. So the chips, when they arrive, they are put into package, and then you cannot do any change as a customer. If the manufacturer decides to change that, maybe for the next batch of 1 million refrigerator, then they can do it, and then they just go to the IC fab again and then change the mask. So we'll see how this is done, the mask RAM, mask written programmable RAM. But people were not very happy, and then people started to develop new technologies to let the customer to program the chip. So it allowed people to program the chip, so it became like programmable RAM. But again, like once you program this, this is fixed. So and we'll see how this is done, maybe internally. So it was allowing allowing the customers to write it once, and then it's not being changed. So either the refrigerator companies could buy this thing. This is done right now. Then, they made this, so it's programmable. So they can sell the same chip to refrigerator companies, dishwasher companies, and some other companies. So it's like a generic thing, which is written once, and then it's being fixed, and then it's not being changed. And later on, people started to request for erasable programmable RAM. Programmable RAM. So in this case, EEPROM, it was called. It was programmed, but it was erasable. So that means you could reprogram, okay? Reprogramming is possible. So, in these devices, you would see that there's a window here, okay? Window on top of the chip. So window allows the erasing of the memory content with UV light. Okay, so the UV light was used to be able to erase the data. Okay, ultraviolet light, and then you could program. Okay, then it could be reprogrammed. So it was not easy operation. I mean, you had to get this chip out of the board, and then you had to erase it, and then using a machine where there's a UV light, and then you could reprogram it and then, put it back to the PCB, for example, maybe with the help of some sockets. But it was, possible. Later on, the technology even further developed, and then there was electrically erasable programmable ROMs developed. Okay, so after this, there were maybe some other techniques, but we will be stopping here. More than ROMs, in fact, we prefer to use RAMs because we want to be able to write and read continuously into the data. So there are more developments on the RAMs, actually, random access memories. So but as a content of the scope of this course is to teach you the basics on this memory. How can you write or read something in the EEPROM? First, this writing, and then how you can erase data and how you can write is going to be explained. And then the idea behind the memory storage is going to be explained. I'll explain those. And then maybe, you can have basic understanding of this concept. So in EEPROMs and EEPROMs, the idea is to have a transistor with a floating gate. Okay, so so that you can use this device for writing and reading. In fact, maybe it would be better to first talk about how the memory is read or how the data is stored. But as the slide that we have here is for that element, which is a critical element. Let's talk about this first, and then maybe we'll talk about this later on, how we can use this device to write and read in a RAM array memory storage. So the basic thing here is to use a floating gate. So the floating gate is is a device, and normally we operate this device with maybe 5 volts, right? So we use this gate voltage to be 5 volts. In this floating gate, you have a polysilicon here, okay, polysilicon, but it is not connected to anywhere. So in normal operation, this device operates like a normal device, and then here is the threshold voltage. V threshold voltage is maybe about 1 volt. So it operates normally, but even though you have a floating gate, what it does is, let's say you apply a positive voltage here. This positive 1, 2, 3, 4, 5, okay, and 6 maybe, is going to create here a negative charge, and 1, 2, 3, 4, 5, 6, and then it will repel the positive charges here, plus 1, 2, 3, 4, 5, 6, And then due to that, there's going to be negative charges here, 2, 3, 4, 5, 6, okay? So therefore the channel is formed. So even though we have a floating gate, the device operates normally. So maybe there's going to be slight change in the threshold voltage, which you can adjust, but that's what happens to the device. Whereas, you know, if you apply a large voltage to the large voltage to the gate like this, okay, and then maybe a large voltage to the drain also. So, you know, with that help of that, some electrons will be able to jump to that floating gate. So what does that mean? Due to that floating gate, maybe I should draw it again here. But you know, this gate, and then this is going to be the gate here, and then there's going to be this one, okay? So so if you apply a very large voltage here, then here you have some what is called hot electrons jump into here. So maybe let's say there are like 3 electrons jump into this region. I should erase this here and then make it like this. So there will be, you know, freely, due to that very large voltage, maybe 1, 2, 3 hot electrons. Okay, can be put into here. How? With very large voltage. Okay, so applying, you know, large voltage here into here, large voltage. So the large voltage manages to attract some electrons from the substrate to jump into that floating gate. And if the oops, I keep making mistakes. Okay. So, but once those are in there, so now when we apply a voltage to here, 1, 2, 3, 4, 5, 6, you know, the matching thing is going to be mostly coming from the hot electrons. So there will be much less number of negative charges here, only 3. So only 3 is going to be, you know, creating only 3 electrons here. And due to that, only there's going to be you know, negative charges here 3. So that means the threshold voltage now is larger, because in order to create, you know, 3 more electrons here, so you have to apply, and then you know, more charges here needs to be applied. So you need to put here like larger voltage is necessary And then if you put larger voltage, then there's going to be, 3 more here. And then there's going to be maybe 1, 2, 3 more here. Therefore, there's going to be 3 more here, okay? So larger voltage, that means your threshold voltage, V threshold new is going to be there. So the device, this device can be programmed. The MOS device threshold voltage is programmable. Either you have it like 1 volt regular, or you can make it maybe, I don't know, 6 volts. Okay, you don't need to have 6 volts, but 6 volts. Okay. So why do we care about this? It will be clear why we care about this when we start seeing the arrays. Okay, but this writing is achieved with very large voltages applied to the gate, select gate. But when you want to erase this, let's say you program it, you make the voltage 6 volt. How? Because you have hot electrons in there. So the hot electrons can be removed with UV light. Okay, so if you apply UV light to this device, then the electrons which are trapped in that floating gate, okay, so they are trapped in the floating gate. Can be removed, okay, with the UV light. So so this is the mechanism to write it and then program it, and then how not to program it. We will be using this in the storage element later on. Okay, so so first let's look at how we can program a device. So in the foundry level, in the manufacturing. So initially, when the manufacturers fabricate the devices, they fabricate, I mean, this is the old maybe technology, but initially they make these fusible links. So let's say these are the diodes, and then you have memory, element here, supply voltage, and then this is the different data. Okay, so this is the least significant, and then this is the most significant bit, and you want to select a row. Okay, so 8-bit data is can be stored here, and then there are 4 different rows of 8-bit data. So basically, the idea here is to store 8-bit, and then next 8-bit, and then next 8-bit, and the next 8-bit. Okay, so when you select this row, the data is going to be available here. Least significant and most significant bit data is going to be available here. So which data? The data in here. So if you don't write anything here, you know, and then there are decoders here. So the decoders are done in such a way that if your, maybe I can, write the decoder concept here. So if the decoder A1 or A0, A1, okay? So A0, A1 is, let's say 0, 0, okay? Then according to this definition here, if this is the case, then the output here, let's say, in here, here, and here, the signal is going to be 0, 1, 1, 1. Okay, so only one of them can be 0. So the idea, normally the decoders make it only one of them 1, the others are 0. But the way that it operates here, let's say if the signal is 0, 0 is applied here, let's say 0 and 0. Therefore, we will have 0 here, 1 here, 1 here, and 1 here. Okay, so that's the concept here. So if the data is row select A0, B0 is selected to be, let's say this one, 0, 1, then the second one is going to be 0. So 1, 0, 1, and 1 is going to be selected. Okay. So therefore, if you apply here, A0, A1, it should be the other way around, right? I mean, it should be 0, 0. Yeah. 0 is going to be that one. A1, A0, sorry. So this should be A1, it's A0. So if A1 is 1, sorry, A0 is 1, so this is 1, this is 0, then that's what is selected. And in that case, this is going to be 1, this is going to be 0, this is going to be 1 and 1. So let's write the next one. Maybe the next one is going to be this. So if you have 1 and 0 selected, the data is going to be 1, 1, 0, 1. So if A1 is going to be 1, and then this one is 0, then the data is going to be 1, 1, 0, 1. Okay, so that's how it goes. Maybe I can select the green here, and then this is 1 and 1. Therefore, this is going to be 1, 1, 1, and 0. So 1, 1 is going to be, maybe here I'm going to write it here. 1, 1, 1, 0. So what happens if one of them is 0? So if one of them is 0, the output, let's say the first one is 0. Okay, so we select this one right now. Let's say we select, I don't know, maybe not this one. So if this one is selected, so if that one is selected, the data that we will be seeing is going to be, you know, this node is going to be pulled down to 0.7. Okay, so you know, that data is going to be read and then it will be pulled down to 0.7. So if nothing is done and then all of them have diffuses, all outputs are going to go to 0. Okay, but we don't want everything to go to 0. So because we want to have ones and zeros written into that 8-bit. So if you want to store a particular data, you start burning the fuses here. Okay, so here the fuses are burned to write a different data. Okay, or alter the stored data. So here, for example, we can burn this fuse and then burn this one. Okay, so when you burn, I mean, here on the right hand side, it is shown like this. Okay, so it's the diode is in there, but it is not connecting anything because it's burned. Okay, so here and here is burned. So we can, depending on what we want to write, so we can burn this. So either this burning is done or the metal revision is done so that these are not put in there. The metals here connecting this one is disconnected in the mask level at the manufacturing site, or manufacturers allow you to do this yourself. So maybe in your factory you can, you know, burn these data and then decide what to store inside. Okay, so let's say this is gone, and then this one is gone, and this one is gone. You want to write another data, right? So let's say this is gone, and then this one is gone, and here all of them are on, and the next one, this one is gone, and then this one is gone, and then this one is gone, and here only this one is gone, and then, you know, like this is going away, this is going away. Okay, so this picture shows you simplified view. After burning the fuses to store the required data. Okay, so what happens if we burn the data? So you know, if you look at this here, the output, okay, so what we have here is just the buffer, okay? So these are buffers. So inside and outside is same. So the data output, so let's say we select which one? Let's say we select this this one, okay? So here, this is applied. So that one is applied means we have 0 here, 1 here, 1 here, and 1 here, okay? So if that one is selected, maybe I should erase this and then write this here, 0, 0, 0, 1, 1, 0, 1, 1. Okay. So if that's the case, then you know, this is going to be off because we have 5 volt here, and the other side, this diode cannot turn on. So for the 0, 0 input, this one is going to be off. So this will be off unless 0, 1 is selected. Okay, so that one is going to be on. When is it going to be on? When we have the second one is selected. So it's going to be on for the other case. Okay, otherwise it's going to be off. So when you select you know, on for 0, 1, okay, so this will be off for other cases. For 0, 1 case, okay. So, but the first bit is not going to be pulled down, and then the data is going to be, output is going to be VCC. So this will be VCC for this case, and then you know, it's going to be 1. Why? When you select 0, 0, the first row is going to be 0, others are going to be 1. So D0 is going to be not able to pull down, so it's going to be remaining at 1. The next bit is going to be 0, so this one is going to be, you know, pulling it down to 0. This one is not going to be pulled down, so it's going to be remaining at 1. And the next one is going to be 0. Why? Because we have this one. Okay. So therefore, all these are going to be pulled down or not pulled down. So you know, this will be pulled down, and maybe I should use a different color here. I don't know, maybe I shouldn't. Okay, so nothing is here, so therefore it's not pulled down. Nothing is here, it's not pulled down. Nothing is here, it's not pulled down. Nothing is here, it's not pulled down. So therefore the data which is stored is going to be first row. The row here is going to be this, okay? So the output data is going to be in hexadecimal format. It's given in here. So it's going to be, 101000101. So it is written once, and then it will be remaining in there. So the second one, it will be the selected. If this one is selected, then this is going to be 0. Why? Because there's a diode in there pulling it down. But this won't be able to pull down because there's no diode, and then it will be remaining always high, even though that line is selected. Okay, so here is 0, this one is 1, and then this one is 0, this one is 0. So this one should be 0, this one should be 1. That's how the data is written here. Okay, so the next one is going to be this one. So if you select this one, so this will be, 0. There's nothing here, so it's just going to be 1. So here, this is going to be 0. This is going to be 0. This will be 0. Nothing is here, so it's 1. Nothing is here, so it's 1. And there's a diode in there, so it's going to be like this. Okay, so maybe I can just complete this. The last one, nothing is here, so 1. Nothing is here, so 1. A diode is 0, nothing, 1, diode, 0, nothing, 1, diode, 0, and then 1. Okay, so this is how you write a data and then read the data. So if A0 and A1, these numbers are selected to be 1, 1, and then that's what you get as the output. So this will be your output for that one. Okay, so as a summary, this is RAM, read-only memory. You write it. Okay, so this burning or burning of the fuses either done. Okay, the writing is the writing data is either done in the IC factory with metal mask, with the metal mask, with the related metal mask. Okay, or done by the customer at the customer side with a special tool. Okay, so a special tool means, how can you burn that? Maybe you apply a large extra current or voltage so that the related pins are going to be, or related fuses are burned to burn the fuses. According to your wish. Okay, is that clear? Sorry, I ran over the time. I was not planning to write this much in here. So we will, I guess, need to give a break. But you know, next time we'll see that we don't have to have diodes in there. In fact, you know, we can use transistors, CMOS transistors, and then write the data again, you know, to pull down or not pull down is decided. So I guess I'll give a break now, 10 minutes break, and then we'll come back to continue. Is that okay?
Okay.
Okay. Merhaba. Kimse var mı?
Merhaba hocam.
Heh,
Merhaba hocam.
ya. Merhaba deyin ya. Yalnız hissediyorum kendimi. Okay. So let's continue. I guess you got the idea here how to write 1 or 0 to a memory stage. You know, this is maybe the older methods where there used to be, you know, resistors here, R, but manufacturing resistors are difficult, as you know, for one thing. And then it dissipates a lot of power when, you know, the output is 0, for example, it cools down the node, and then the voltage there is 5 volt divided by R is large. So people decided to implement the same idea, but same, but differently. And the way that, you know, we write the data, for example, pulling down this node is done with a transistor. So initially, either you put here maybe everywhere transistor, and then put a fuse here, okay, for example. So the fuse here is not burned, but the fuse here is burned. So therefore, maybe I shouldn't do that. I'll be erasing the fuse here, okay? So normally there are all these transistors here, you know, multiple transistors, but the fuse is gone. And then this one, it's in there. This one, there's a transistor. I'm drawing this way so that's easier to see. You know, normally this is connected here, this is connected here, but it's burned. So since it's burned, it's not possible to pull that node down. And there's a, I guess, maybe mistake here. This should be called pre-charge bar. So the pull-up is done not with the resistor, but pull-up is done with the MOS transistor, PMOS transistor. Okay, so here is PMOS, and then the way that the signal is created is like this. So you normally have high voltage here, pre-charge bar. Pre-charge bar signal, okay? So normally it's going to be high. When the pre-charge comes, so that means pre-charge bar goes to low. So the signal now, not only the transistors are here for pulling down, but for pulling up, cycle is different. So, you have the signal changing. Maybe I'm going to write one more to define or let you know what is happening here. Okay. So when the pre-charge is high or goes to low, so let me draw here the other signals. The other signals are going to be maybe in zero signal, and zero signal is going to be low. Maybe it will go high. Let's say first we will be reading this. Okay. And then we will be reading into here. Okay, only two of them we will be reading. Oh, there is one more, so why not read one more? So we'll be reading here. And then this one we'll be reading here. So this is the time domain, of course, different times here. So this is in 1 and in 2. So the outputs, bit 0, and then this one. The bit 0 is going to be, initially, we don't know the value of it. I mean, it could be high or low. So we don't know what it is. Bit 0, bit 1, bit 2, and then bit 3. So initially, probably it's going to be, let's say it's 0. We don't know its value. But when pre-charge bar becomes 0, so that means here when it becomes 0, so this is where it is, that signal, then all of them goes high. Why? Because it's pre-charged. So this will be, goes to high, and then they will be remaining high. Goes high, goes high, and goes high. All of the outputs. And then they will be remaining high until here, Okay, so they will be remaining high because there is nothing to pull them down. Okay, but when this one becomes high, so bit 0 is pulled down because this turns on. So let me maybe select a different color here. So when this one becomes high, 1, this is 0 and 0. Then bit 0 is going to be pulled down to 0. Okay, so it will be remaining 0. So output is going to be 0. And then bit 2, there is nothing to pull it down. So there is nothing here to pull down. So it will remain at high. So the data is going to be 1. And then bit 2, what happens to, did I make a mistake here? No, bit 0 goes down. Bit 2 cannot go down. Bit 3 can go down. Why? Because of this transistor. So this transistor, goes 0. And the other one here, nothing to pull down. So it's going to be remaining at high. So the data is going to be like this. Okay, so in the first line, the data is 0, 1, 0, 1. So how did we initiated that? Because of this ing goes to high. Okay, so when that goes to high, the data at the output is going to be 0, 1, 0. So next, there's going to be pre-charge again. So the pre-charge cycle starts, so they all go back to high. They all go back to high. This is already high. This goes to high, and this is going to be remaining high. Okay, so they go high, 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 and high. And they will be remaining high until the next reading is started. So if you want to read this one now, let's go to that one. Maybe say it this way. So now we go to this one, high. So 0, 1, 0. Then the bit 0 is going to be pulled down due to this. So bit 0 is going to go down. And then it will be remaining until here. So bit 1 is not pulled down due to the second line. It will be remaining at high. And then bit 2 is going to be not pulled down, but bit 3 is going to be pulled down. So it will be pulled down. So the data is going to be 0, 1, 1, and 0. So the data stored here is 0, 1, 1, 0. So maybe similarly, we can, draw this one and this one. Now 0, 0, 1 comes in here. So the data stored is going to be 0, 1, 0, 0, 0. So, and that means initially they will be all going up. Again, with the pre-charge signal that goes up until the read comes in here. So this will remain up, this will remain up, this will go up. Okay, they will be all 1, 1, 1, 1. And then the last bit, it's going to be not pulled down. So the blue one is going to be like this, but this will be pulled down. This will be pulled down, this will be pulled down. So therefore the data is going to be 1, 0, 0, and 0. So in the time domain, you can select this and then, read the data. So you can consider this to be maybe bit 0. It's behaving as if the bit 0 behaving is like what? You can write this in a different way. Bit 0 is, if you look at this bit 0 is like pre-charge. Pre-charge bar, and then you have as if you have two inputs here. So one of them is in 0, the other one is in 1. So you can say that it is NOR of in 0 in 1 bar. If you look at bit 1, there's only one transistor here. So it is functioning as if it is in 2 bar. And the other one is in 0 or in 2 bar, or in 1 or in 2 bar. So that's the kind of the function that you generate. But the bits, the stored data is going to be like this, okay? So how did we store the data or change the data? By burning the fuses here, maybe by putting a transistor here and connecting this one here, and then the fuse is burned, okay? So it is pulled down or pulled up, okay? So, but another way of doing this is not burning that fuse, but change the threshold voltage of this transistor, for example. This transistor, okay? So for writing 1, okay, in order to write 1, this transistor, let me put it this way, for bit 0, let me write it for bit 0. For bit 0, normally this is the pre-charge bar signal, and then VDD. So we use here in 0 input, and the transistor is like this, and then we say here in 1 input and the transistor. Now this last one can be also connected here in 2, but this threshold VT2 is 6 volts. So instead of connecting or not connecting, by doing this, okay, we can either not connect a transistor. Let's say this is M0, M1, and M2, okay? So connect a transistor or D transistor M2, either not put a transistor here, or here, either not put a transistor here, or burn a fuse, or change the threshold voltage of M2 how? With hot electrons, right? By using a floating gate transistor. So like this thing that I told you. So this VT new is going to be selected. So VT new, maybe I should say new. And then write it that way. Okay. So that's the concept here to program it. Okay, programmable. Programmable transistor means, you burn the fuse here, but it's done once. So you cannot rewrite that one. But if you change the threshold voltage, then it's going to be EEPROM. Okay, so this is the concept in EEPROM. Okay, so this is the concept. Burning fuses is PROM, programmable approach. Okay, so burning the fuse, the PROM approach. In the PROM approach. It's burned. It's in there, the transistor, but the connection is burned by the customer. So I guess I already explained this concept here. So this should be pre-charge bar, by the way. So pre-charge bar is low. If it is low, pre-charge bar signal, it's going to be low initially, and then it goes to high, and then it goes to low, pre-charge bar. Okay, so here the output Z is going to be initially high, and the decision is made here, or it's going to be F of AB, and that's going to be, the decision is A or B bar. So we don't know what it is, but when the pre-charge bar goes to low, okay, so output is pre-charged in here. So until the data is read by selecting this one. Of course, this signal is also synchronized with another timing. Let's say you select, maybe you have 2 clocks here. Now I'm confusing you maybe a little bit, but so this is phi 1, and then this will be another clock cycle, phi 2. So this one is selected to be synchronized with, how should I say here? When it goes high, there should be phi 2. Okay, and then this should be A times phi 1. So therefore, B times phi 1. The signals are ended, so they happen to be different times, the read times. So this pull-up doesn't have to be pre-charge. This one, alternative to pre-charge concept. Okay, so this is like pseudo NMOS concept. So you here select the weak transistor. Okay, so if the so this is weak transistor on all the time. Okay, so we learned that, you know, if these are all off, output is going to be pulled up to VDD. But if any of them is high, you know, these signals, the output will be pulled down to low voltage. So V output high will be equal to VDD, but V output low is not going to be equal to 0. Whereas here, V output high is VDD, V output low is 0 volt. Okay, why? Because pre-charge only charges certain times, not all the time. So here there's going to be static power dissipation. When output is low. When output is low. So I mean, this is one of the source of static power dissipation, for example. And here, A or B bar is going to be the signal. So in summary, you either do this pre-charge bar, pre-charge concept to write the data, or you can make something else and do this thing in NMOS technology, if you had the NMOS technology, okay? So this was useful for NMOS. Where depletion transistors are possible. Okay, so not possible in CMOS technology. Okay, so in this approach, this was different than here the concept is different, but you can understand that the outputs are here. C1, C2, C3, C4, a different approach, okay? But you can write C1 to be R3 bar, okay? And then C2 output will be equal to R1 times R4 bar, okay? So basically C3 is R2 R4 bar, and then C4 is R1 R2 R3 bar. Okay, so this is in fact NAND based ROM. So you can do it either this one. Okay, so this is NOR based NOM. Or you can make it NAND based RAM. So that was also used in the past. You know, here bit 0, as we discussed, is going to be in 0 or in 1 bar. So that's also another implementation. In these devices, you know, these transistors are going to be available, and before programming, and then you decide to either burn or increase the supply. So here is another pull-up, okay? Pull-up. So this is like what we have seen before. This one is used as the pull-up. Again, output high, where V output high is going to be equal to VDD minus V threshold of N. V output low is not going to be 0. So that's not a good one, but it is possible. Why they put here one more this device, I'm not sure. In this, I mean, these are for pulling up, but this node is weird. I mean, I don't know why they make this thing. Maybe for writing or burning, or you know, changing the threshold voltages, and that's necessary. You know, that kind of thing is allowing us maybe to give a high voltage to some of the nodes by selecting it. And that's why, you know, probably they put it in here. So I'm not really sure. Okay, so I mean, there people make different things, as you might notice here, and you know, different things can be written. So I guess this is enough. You know, different pull-up concepts. Can be used. Okay. As we learned, for example, pre-charge, or NMOS transistor or pseudo NMOS, so PMOS, like used like pseudo NMOS, or resistor, whatever. And then you know, the active thing can be written, programmable, erasable, and maybe one thing that I should talk here, we talked about erasable prom, and then we said if we apply large voltage to the select gate, then the floating gate will have attract some hot electrons, and then they will be remaining in there. And then with the help of UV light, we can erase that, and then, you know, that electrons trapped in that floating gate, you know, get enough energy to go back to silicon down, okay, to the substrate. But, you know, they managed to do that, removing that hot electrons electrically also, not with the UV light. So if they do that, it was possible to obtain electrically erasable. Okay, so they managed to do this electrically erasable. Okay, so that's, I mean, they change threshold voltage, and then threshold voltage goes back. Okay, so this is due to hot electrons. In the floating gate. And then, you know, it is discharged by UV, erased by UV light or electrically. Okay, if it is UV light, it's EEPROM. If it's electrically, EEPROM. So I guess this is enough for the read-only memories. And there's RAM, the memory, and I'm afraid 5 minutes is left, but let's start talking about it. So in this device, we will be able to write something and then read that output. So that's the concept. So you know, we typically take you know, rows and columns, so we have many bits next to each other. So if you want to read the data from the first row, you select that one and then send maybe high there. All others are going to be low. Okay, so then you know, the data wise, this is going to be maybe 1, but then this is going to be 0, 0, 0, 0, 0, 0, 0, 0. All of them are going to be 0. Okay, so that you can read this one is red, or you can write to that. So with the help of row decoders and then address decoders, you can read it. But sometimes, you know, in the arrangement here, you know, you make this one for the least significant bit, or let's say this one is least significant bit, and then the next one is going to be next bit. And so you can, you know, place these things next to each other, so you don't have to read the row here. Okay, so therefore you need maybe column address decoder, row address decoder. So in this one, you know, there was only one decoder, but in here there are 2 of them, so that, you know, least you know, this block, the whole thing is for, this whole thing could be for only least significant bits, and then the next one is going to be the next one, or there might be like, you know, the read structure could be like the data here. So the first two is going to be in this, and the second two is going to be in another one. So the arrangement can change. That's the bottom line for the RAM structures. So they do this, whatever is more convenient, they do it that way. Okay, so, and then there is an extra thing here, which will be hopefully clear, the sense amplifier. Okay, so row decoder, column decoder, and sense amplifier. And the idea is this one. This is called static RAM. Static RAM means as long as the power is on, the data is stored, and you don't lose the data when you read it. Of course, you don't want to do that, but why? Why am I talking about that? Because the next things that we will be seeing, when you read the data from a pixel or memory cell, then the data is lost and you need to write it back. But here, you don't have to do that. And it's going to be hopefully clear when we talk about the other ones. I mean, this is now trivial. So, you know, this each cell here is called a memory cell, okay? So they can be either 0 or 1. And then the inside can be static RAM, okay, or SRAM, or dynamic RAM. It's going to be maybe DRAM. Okay, so each cell, memory cell, can be either, or stores either logic 1 or logic 0, and that's what it is. So this is to speed up the read write okay, and I guess we don't have time left, but you know, here we use both the data bit line and then bit line bar, and we will be talking about this tomorrow then, but basically we have this kind of memory arrangement here. So if this is bit is 1, then bit bar is going to be 0. So that is stored until you want to change it. So this is how it's done. So this is bit, this is bit bar. So you can write into each pixel or memory cell and then read it later on. Okay, so I will continue tomorrow, and hopefully, you know, we'll finish this and also maybe start the new subjects tomorrow. Okay, sorry, you know, took a long time today to give the details. Tamam mı arkadaşlar?
Tamam hocam. Tamam hocam. Hocam